Moving on, discussing how we define rates, we want to talk about the concept of related rates. So we know that we're looking at changes in concentration to characterize the rate of a reaction. And we know that changes in concentration are going to be based off changes of amounts of my different substances. The reactants are reacting. I am going to be decreasing the amount of reactants and increasing the amount of products. The changes in those two things are going to be related via stoichiometry. If I look at, say, this reaction, for every 2 moles of NH3 that is consumed, I know that I will get exactly 1 mole of N2 that is produced, right? That's the stoichiometry relationship that comes out of my balanced coefficients. I can then take that and come up with relationships between the rates. When you do an experiment, you are measuring the concentration of one of your substances and seeing how that changes over time. And so you could measure either the rate of ammonia or the rate of N2, right? You can measure those two different things, but they're going to be directly related. What that means is you don't need to measure both of them. If you measure one of those rates, you will be able to calculate the other based off this relationship. So the stoichiometry is right here. It's 2 moles of NH3 consumed for every 1 mole of N2 produced. So you'll note it's -1/2 times the rate of NH3 equals the rate of N2. So that -1/2 term, we can decompose first the negative sign. NH3 is a reactant, so its concentration will be decreasing, whereas the concentration of N2 will be increasing. What that means is I know that this number is going to be negative. The rate of NH3, because it's a reactant, that number will always be negative, and we know that the rate of N2, because it's a product, will be positive. So in order to make them equal, I need to put in a negative sign. Okay, so that's the first thing, that there's always going to be a different sign in the rates between reactants and products. Then the 1/2 comes from the coefficient. You will note there is a 2 in this reaction. There's a 1 in front of N2. So basically what that tells you is you know that there will be 2 of these molecules reacting for every 1 molecule here that you make. That means the rate of NH3 will inherently be larger because the coefficient is larger in the reaction. And in order to normalize them, in order to make them equal, you divide by the coefficient. N2 has a coefficient of 1 in front of it, so you just divide by the 1, which doesn't show up. So the two things we want to account for when relating rates are the sign, based on which side of the reaction it's on, and then whether or not it's whether or not what the coefficient is to normalize it out. This is in general going to be true in terms of relationships. So for every 2 moles of H2 consumed in, say, this reaction above, 2 moles of H2O are produced, right? We can just read that off the coefficients. And so that means because they have the same coefficient, their rates will have the same size, but they're going to have a different sign because hydrogen is a reactant and H2O is a product. In general, reactants, because they always have the negative is going to be in here, this value will be negative, is why we put the additional negative sign in front of them. If we were to relate, say, O2 and H2O, we know that we need to account for those different coefficients, right? The fact that they're different coefficients mean they will have a different, the rates will have a different relationship. So we have all these different numbers. We want to put them into a single value for each reaction. We call that the overall reaction rate. So this is a single number that characterizes the entire reaction. When you do an experiment, you measure the concentration change of one thing, as a reactant or a product. But you want to get a single number that anybody studying that reaction can use and compare, right? Person A might be using one of the reactants, person B might be measuring one of the products. You want to get a single number that you can both compare. The overall reaction rate should be always positive, and the units are concentration over time. This is always going to need to be your kind of description of what we're dealing with of when we're describing an overall reaction, a single number that is always positive. So this is going to be the first place where we're going to start to see a generic reaction. You'll note I have little a plus little b, big B becomes little c, little d, big D. These are just these are functioning like variables describing a generic reaction. The capital letters just represent a formula. So A is just a chemical formula, B, capital B, just a chemical formula. The lowercase letters are coefficients, so those are like mathematical variables. That lowercase b could be anything, 1, 2, 3, 4, 5, 6, 7, 8, doesn't matter. And we can take that generic description and we can define the rate for a chemical reaction based off any one substance. So first off, what we can see is that if we wanted the the overall reaction rate, which we just call rate, we could measure the rate of change of one of my reactants or one of my products, and then we could compute those together to get the overall rate. So if I put a number in, we can divide by the coefficient and get the overall rate. The other thing that we can do is we could relate any pair of reactant or product. So say it may be easy to measure the rate of change of C, of compound C, but you're interested in the rate of change of compound B. You can measure whatever is easiest and relate it to all the others because they're all linked together via stoichiometry. So we can always develop this relationship for any reaction and get every single compound into that relationship. So let's do an example, see what this looks like. Define the overall rate for the following reaction based off each reactant and product. So it's C2H6 plus 7O2 gives me 4CO2 plus 6H2O. So let's write this out, see what it looks like.
So when we want an overall rate, we want to define the overall rate, we're looking for an equation that would let us get a single number to describe the whole reaction. And we can do this for each of the components. So because I have reactant, product, because I have 4 things in the reaction, I know that I have 4 separate, basically, relationships here. And so, I can define the rate, experimentally, we define the rate based off each substance. So we can imagine that we have the change in the concentration of C2H6 divided by the change in time. So this would be the rate of C2H6. How is it changing? And so I want to take that and from that compute out an overall rate for the whole reaction, right? That single number that describes the whole reaction. So one of the things I know is that this is a reactant, so its concentration is going to decrease. This number is going to be negative. I want that to be positive, so I put a negative sign out there. The other thing is that I have that coefficient, right? Everything has a coefficient. So what I want to do here is make this a 1/2. So I want to divide it by 2. Basically, every time the reaction happens, 2 of these react. So basically, the change in that divided by 2 gives me how many times all of these reactants become all of those products, a singular number. So I can define it for that. I can also define it for O2. And I know, again, the rate for O2 is delta concentration O2, delta T. That's my rate of the rate of change of the concentration of O2. It's a reactant, so it's going to get a negative sign. And this gets 1/7. Whatever the coefficient is just gets put down in the denominator of that fraction. I could do it for CO2. I know that delta concentration CO2 change in time. In this case, this is a product, so the concentration is going to be increasing. This number is going to be positive, so rate will still be positive, but I still do need to divide by the 1/4. And then finally, I could do H2O. Rate is equal to 1/6, change the concentration of H2O divided by the change in time. And so any of those are going to work. And it's important to note that when I write all these equations out, all these relationships, that this rate is the same as that rate, is the same as that rate, is the same as that. The idea is when you perform an experiment, you have 4 different concentrations you can follow over time. Right, you could do C2H6, O2, CO2, H2O. Someone else who is measuring the kinetics of the same reaction may choose a different compound. And as a result, they would get a different number. But you want to convert all of those into some standardized overall rate. How many times do all of these reactants become all of those reactants? And so say you computed the change of the concentration of just this, you would take that number, multiply it by -1/2. So, it would actually look like, this is, mathematically -1/2 times that change of the concentration C2H6 divided by change in time. So this is like what we were looking at in previous examples of when you take your experimental data and you calculate like the slope, or you figure out your instantaneous rate. Whatever it is, that's the number that you measure or calculate. You just multiply it by -1/2 and you get the rate.
We can see these relationships in action when we look at a graph of the change in concentration over time. So if we return to reaction of NH3 becoming N2 and H2, one of the things we can see is that NH3 is a reactant. Its concentration is decreasing over time, whereas H2 and N2 are products, so they are increasing over time, which is good. That's what we would expect to see. When we take a look at it here, we can also see that, the increase in H2 is really big, whereas the increase in N2 is relatively small. And that is because there's a 3 in front of H2. So there's a 3 in front of H2, which tells us that we'd expect that to increase faster. So for every 1 of the N2 molecules we make 3 of the H2 molecules, which means the slope is 3 times higher than this slope, because the rate is 3 times higher. And then the NH3, it is negative, right? So we expect it to be negative, and so they've taken the negative of it here to get the value, and then it's kind of an intermediate number. It is 2 times the rate of the N2, so this is 9.7 times 10 to the 6th. Multiply that by 2, you get the 1.94 times 10 to the -6. If you multiply by 3, you get the 2.91, or close to 2.91. And so these ideas, they're all showing the same reaction. It's the same chemistry that they're all describing, but they're going to show it in different ways. So we want to get a single number that comes out of all of these, and how we can if we took all those numbers on there and divided by the coefficient, we would get the same singular number, which would describe the rate of the overall reaction. Participation 130, question 1. It takes 75 seconds for the concentration of O2 to fall from 4 molar to 3.6 molar in the following reaction. What is the overall rate of this reaction? 2NO2 plus 3O2 becomes 4NO2. This is the first question on participation 130, due Friday, January 30th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, it takes 75 seconds for the concentration of O2 to fall from 4.0 molar to 3.6 molar in the following reaction. What's the overall rate of the reaction? The reaction is 2N2O plus 3O2 yields 4NO2. Okie dokie. We actually had a question for participation 130 in this video. I told you there'd be some. We are over halfway through, so I'm guessing there'll be a decent density of questions in the back half of this set of videos, but we won't know until we watch them. See you there.